The movie Avatar imagines a future where human technology has reached an advanced and highly specialized level, especially in the field of aviation and military engineering. Among the most striking elements of this future are the aircraft used by humans on the alien moon Pandora. These machines immediately capture the viewer's attention because they look futuristic, powerful, and visually believable at the same time. Unlike many science fiction films that rely purely on exaggerated or impossible designs, Avatar presents aircraft that feel functional and purpose-driven. This realism naturally leads to an important and fascinating question. Could these aircraft actually exist one day? Or are they nothing more than beautifully designed fantasy machines created solely for cinematic impact? To answer this question properly, we must step away from the mindset of a movie viewer and adopt the perspective of an engineer. Engineering does not care about aesthetics, symbolism, or storytelling. It is governed strictly by physics, energy requirements, material limits, aerodynamics, and efficiency. An aircraft either works within these rules or it does not fly at all. What makes Avatar particularly interesting is that it does not take place on Earth. Pandora is a completely different world, and this difference is critical when judging the realism of its aircraft. Pandora has lower gravity than Earth and a significantly denser atmosphere, two factors that dramatically change the rules of flight and make aerial vehicles far more viable than they would be under Earth's conditions. Lower gravity means that aircraft on Pandora do not need to generate as much lift to stay airborne, reducing the overall energy demand. At the same time, denser air allows wings and rotors to push against more air molecules, increasing lift efficiency and improving control at lower speeds. Together, these conditions make hovering easier, reduce stall risks, and allow for heavier payloads without requiring impossible levels of power. This does not mean that anything can fly on Pandora, but it does mean that designs which would be impractical or inefficient on Earth may become realistic under Pandora's environmental conditions. When Avatar's aircraft are judged using these rules rather than Earth's, the line between science fiction and engineering reality becomes far more blurred. The SA-2 Samson transport aircraft is the best example of this balance between realism and imagination. The Samson serves as the primary human transport vehicle, carrying soldiers, scientists, supplies, and equipment across Pandora's dangerous terrain. Its design features two large duct rotors mounted on either side of the fuselage, allowing vertical takeoff, hovering, sideways movement, and precise landings in confined spaces. These capabilities are not fictional. Modern helicopters already perform similar maneuvers. Duct fan technology exists today and is actively being developed for drones, military aircraft, and future urban air mobility vehicles because it offers improved safety, noise reduction, and efficiency during hover and low-speed flight. From an aerodynamic and structural standpoint, the Samson is well-balanced and logically designed. Its center of mass aligns closely with its lift sources, reducing instability, and its wide rotor spacing improves control. The real challenge for the Samson is not whether it can fly, but how it is powered. Hovering while carrying armor, weapons, passengers, and cargo demands a continuous and enormous supply of energy. On Earth, such a vehicle would be extremely expensive to operate and limited in range. However, on Pandora, the reduced gravity and increased lift efficiency significantly lower power requirements. When combined with advanced engines, lightweight composite materials, and future energy systems, the Samson becomes not just believable, but arguably the most realistic aircraft in the entire Avatar universe. The Scorpion gunship shifts the focus from transport to combat, and its design reflects speed, aggression, and intimidation. Equipped with four large rotors arranged around a compact central body, the Scorpion resembles a mechanical insect, a design choice inspired by agile flyers like dragonflies. In nature, dragonflies are masters of the air, capable of hovering, rapid acceleration, sudden direction changes, and extreme stability. The Scorpion attempts to replicate these biological advantages through technology. Quadrotor systems already exist in modern drones, and attack helicopters are well-established military platforms, so the basic concept is not impossible. However, scaling a quadrotor system into a manned, heavily armored gunship introduces serious engineering challenges. Multiple large rotors create complex airflow interactions, where downwash from one rotor interferes with others, leading to turbulence, vibration, and uneven lift. These forces place immense stress on the aircraft's structure and mechanical systems. Synchronizing all four rotors during high-speed maneuvers and combat situations would require extremely advanced flight control computers and constant maintenance. While Pandora's environment helps reduce lift requirements, the Scorpion would still be inefficient, expensive, and mechanically demanding, making it suitable only for short, high-intensity combat missions where agility and firepower outweigh efficiency. Paragraph 8. The Sea Wasp represents an even more ambitious design by attempting to combine two fundamentally opposing flight concepts: vertical hovering and high-speed jet flight. In real-world aviation, helicopters are limited in speed due to rotor aerodynamics, while jets achieve speed through fixed wings and forward thrust, but cannot hover. Engineers have spent decades experimenting with VTOL jets and hybrid aircraft, but these designs almost always suffer from serious compromises, including excessive fuel consumption, heat management issues, and extreme maintenance complexity. The Sea Wasp would face these same problems, even on Pandora, because combining lift systems adds weight, mechanical stress, and failure points. Paragraph 9. Despite these challenges, the Sea Wasp could still function in limited roles. Short-range patrols, rapid response attacks, or coastal operations might justify its existence, especially in an environment where air resistance and gravity work in its favor. However, it would be dangerous to operate, costly to maintain, and inefficient over long distances. This places the Sea Wasp in a gray area between realism and fantasy. Technically possible under ideal conditions, but far from practical as a mass-produced or long-term operational aircraft. Paragraph 10. The Dragon assault ship is where Avatar fully embraces spectacle over engineering reality. This massive aircraft is heavily armored, packed with weapons, and expected to hover and maneuver like a helicopter despite its enormous size. Physics imposes strict limits on such designs. As size increases, weight and structural stress grow faster than lift, making stability and control exponentially more difficult. Multiple massive rotors would create extreme turbulence, vibration, and mechanical strain, while no believable engine system could provide enough continuous power to lift, maneuver, and arm such a machine, even on Pandora. When all of Avatar's aircraft are compared, the conclusion is clear. The Samson is highly realistic. The Scorpion is possible but inefficient. The Sea Wasp pushes engineering to its limits, and the Dragon is pure science fiction. Avatar succeeds because it blends real engineering principles with imagination, creating aircraft that feel believable enough to immerse the audience while still delivering unforgettable cinematic impact.